the issues that we have when we want to deepen neural networks. So the first issue we have seen that, deep neural networks, like for example, this one, the blue network that has 56 layers, it has a worse training or a larger error compared to the network with only 20 layers. And this also applies to the testing error. So when you have the testing data, we have a worse, I would say, generalizability to unseen data using the blue network. So here you can also see that the test error is much higher than the 20 layer network, okay? So this is what we call, we called it bad learning behavior or training behavior as the network deepens, okay? Another phenomenon that we observed based on empirical data is called shattered gradients. So as the network also deepens, we add more layers to the network, then we have seen that the correlation between the gradients, the gradient change and the data change here, it decreases. So for example, when you have a network with only 2 hidden layers, you have a very high correlation, which means it changes in the input. They correlate with changes in the gradient, which is a nice behavior to stipulate. And then here, what we have for the 24 hidden network, we see that the correlation is 0. The autocorrelation is 0, which means that the gradients are not correlated anymore with the input data, so they are shattered. So if we have, input sample, training sample xi and training sample xj, we'll have completely, like shattered gradients that are not correlated. So they're scattered in the space. And we can see this here also with the gradient of the output dy with respect to dx. And we have observed this zigzagging or shattered gradient phenomenon as we plotted the gradient against the input value right here. And this is for 24 hidden layers. So to solve these two problems, problem 1 and problem 2, that we have seen, which is bad behavior during the training stage as we add more layers. Also, the shattered gradients that we have as we add more layers. So how could we possibly solve that? So we introduced the concept of a residual or a skip connection. We did not discuss how the residual connection would fix this, but we kind of, gave an idea about the potential of this residual connection that we introduced right here, where we are trying to learn an additive function or layer, okay, F1 at each layer. So here at layer 1, that we will add to the input to, get the final output, okay? So in this residual network, we have seen that we have different paths of different lengths from X to Y. And this could be viewed as an ensemble of 4 networks. So we have the blue network, the gray network, the orange network, and the white one. And these basically 4 networks, we add them up, and as we add them up, we get the final Y. So our hope is that with this kind of stacking of nested networks, we will regularize the learning of the network, and we will kind of diminish or decrease the fluctuation of the gradients over here. So this is basically the idea is that as the network gets deeper, right, the gradients may explode towards the end, or they may get, they may vanish. So to avoid that, we hope that some of these shallow networks compared to the final one, that is the deepest one, right? So will contribute to this regularization or toning down of the changes between layers in the gradient magnitude. Okay, so that's our hope. Now we will see what is really happening in this residual network. But before we go into that, I would like to cover an important point. So just hold on to the idea of the shadow gradients, the depth of the network, and this power of this residual connection. And we'll talk about the order of operations in a residual network. So here, usually when we have a residual network, there is an order in which we introduce the network operations. So we know we have a linear combination, right? So it could be also the convolutional neural network, the convolution in the case of a CNN, if we're using a CNN, right? It could be a simple, multiplication and by, the weights that we're learning, and then we're summing, so we're aggregating. So these are the operations that we use in the linear layer. And then we introduce nonlinearity, and nonlinearity here is, for example, manifested by the ReLU function, okay? So this is the typical or conventional order that we use in fully connected networks, in MLPs, CNNs, right? So the usual order of linear transformation or convolution, followed by a ReLU, nonlinearity, means that each residual block can only add non-negative quantities. Okay, so this is the usual order, as I mentioned. It could be a convolution or a simple linear transformation. We have a ReLU nonlinearity here. However, when you apply it to a residual network, and the residual network has this kind of residual connection, what happens is that we can only add up non-negative quantities. Why is that? So let's think about it. I want you to look at the network. You can answer this question by yourself, because what goes into into this basically addition operation. So we have two things here. We have the input data, right? So we have the input data, and we have the data that comes out of the ReLU, okay? So the data that comes out of the ReLU is always positive, all right? So somehow, some negative values that may exist in the X, they will disappear. So if you have, for example, I'm just putting different values here. If you have something like -1 in your X, right? And you're gonna add the output right after the ReLU right here. So this is the output that we're looking at. This output may have a value of 2. So it's always going to be positive, okay? So because of that, it will kind of clip the negative values. It may lead to the suppression and sometimes the emission of the negative value. So the suppression of the negative value in the first layer, in layer 1. But if you stack these and you repeat that multiple times, so you have X, and here I'm going to put these, so you have linear, the linear layer, and I'm gonna just redraw over here. And then we have a ReLU, okay, and then ReLU. And let's do that multiple times. So what happens is that we're feeding this, we're doing a linear layer ReLU and then a plus, so we're adding the residual connection over here. So here there is a suppression, but in the next layer, we are taking, so we have also a residual connection here, we're taking the output of this layer and we're adding it to this one after a ReLU. So what's going to happen is that this output is positive. So let me choose a different color. So this output right here is forced to be kind of positive. And every time I'm taking a ReLU, I'm adding more positive values. So even if there are some negative values, they will disappear because I'm always adding some positive values. So if I have -3, maybe here I have 2 and I have 1. So in the next layer, I'm gonna clip or make this negative value disappear. So somehow, because we are putting the ReLU right before, like the output of this layer, then the negative values or the negative quantities will not remain. So they will disappear, okay? So this is a problem if we have negative data and we want to predict negative data. So for example, let's say you have a negative signal here that has negative and positive values. So like, for example, an EEG, okay? And this is 0, and you want to predict the sequence at, so this is from 0 to t, and you want to go from t to t plus 1 to big T, right? So to do this kind of prediction, your model needs to predict both negative and positive values, all right? So now how can we solve that? So this can be solved if you think about it. So there are different options. So maybe you need to think about this ReLU. Maybe we can move it somewhere else because this is forcing the negative values to disappear, right? So the problem comes from this element right here, this operation. So logically, when you start thinking about the etiology or what causes the problem is you want to remove the cause of the problem, okay? So let's look at, an alternative solution. So this is another solution. So in this solution, basically, we switch the order between the ReLU and the linear layer. So we put the ReLU first. So the ReLU comes first, and then we have the linearity here, and we do transform the data before, okay? So here, when we add up the data, we add up the data before the ReLU. So this data might have, negative and positive values, okay? And we add it right here to the output of the linear layer. So somehow we are preserving the possibility of having negative values. So with this reverse order, so let's choose a different color, so orange. So with the reverse order, both positive and negative quantities can be added, all right? However, we must add a linear transformation at the start of the network in case the input is all negative. So if the input is all negative, okay, so we don't want to pass it through a ReLU. So imagine what happens if your input is all negative. So if I have, so this X has all negative, values, negative 0.7, negative, 11, etc. So this is my vector right here. And if I pass it through a ReLU, so I'm going to take the, if I take the maximum value of this, of course you have multiple channels, but you can think about taking the max of 0 and X itself. So what you're gonna do is you're going to 0 all of these. All right. So if you 0 all of these negative values, you somehow make them disappear. And that is not a good, it's not a good operation to perform right here, because you're going to, later on when you do some linear transformation, okay, so you're going to combine some values, you're going to find yourself combining a bunch of zeros, because it's actually the operation we apply here is 0. It's max 0x, and X is negative, so we're going to end up always with zeros. That's max, the ReLU function, okay? So you can think about it logically. So whenever you guys are going to put blocks, and you need to think about the order in which you're stacking blocks, and the order in which where you want to add, your skip connections, beginning and end. What is the starting point of your skip connection? What is the end point of your skip connection? And you need to know your data. So the rule number 1 is you need to know if the data has some negative values or not, okay? So now why we need to linearly transform? So we do some linear transformation, and with the linear transformation, somehow we can change the distribution of the data. So with the linear transformation, we can have some negative weights, and if we have some negative weights, somehow we can produce, so let's say you do a weighted combination, and when you do a weighted combination, you will have here multiplied by -2. So that's the weight that you're learning for the linear combination, okay? And then when you do that, you're gonna get some positive value. So somehow with this linear transformation, you're hoping that you're going to create some diversity in your data. So when you feed it to the ReLU, you will not end up with this case. Okay, so you're learning. Everything is learnable, of course. Your W is learnable. The linear layer here is also learnable, but you don't want your network to crash from the get-go, from the beginning, okay? So let's remove all of these guys and then look at the next scenario. So in the next scenario, we're going to have a different approach. So here we have basically a third case where we can order the sequence of operations and also the, change the beginning and the end of the residual connection. So in this case here, we see that it's common, like for a residual block to contain several network layers. So basically, instead of doing two single operations, you can stack up operations. So you can do, for example, you start with, of course, a transformation right here. So here we don't have the X, but you do a linear transformation depending if the data is negative or positive, but you can start with a linear transformation somewhere at the beginning, and then you can stack these up. So of course, you don't start with the linear layer and the ReLU for the reason I mentioned earlier. But you start with a ReLU and then linear layer, and you can stack these up. And usually this will allow you to capture more complex transformation or more complex change between, remember guys, the H. So if this is, H3 and the input is H2, so H3 minus H2 is F that takes H2, and we have phi3, the layers. So this is what we have seen in the first, in the previous lecture. So this delta, this change here may be very complex. So we want to learn a complex F parameterized by phi3. Phi3 has all the weights in this linear, in these two linear layers plus the biases, okay? So somehow you don't want to capture a simple or reductionist kind of change. You want to capture a complex transformation from H3 from H2 to H3, from H2 to H3. So you stack up these nonlinearities in linear transformations, okay? So I hope this is clear. Now, in this case, let's move on to the next step. So as I mentioned here, I just wanted to talk about the order of operations in residual blocks and how we can also stack or contain, a single block can contain several nonlinearities and also linear transformations. Next, let's go back to our the problem of the shattered gradients, the problem of the deep network, okay? So what we have noticed is that the residual network may not in this current, in its current design may not solve the problem of depth. So the question here that we're asking, can we increase the network depth arbitrarily? Arbitrarily, it means randomly. So we can make this network go deep and deep and deeper and deeper and deeper, right? So the question here is very valid. So let's try to answer that. So there are two things that we need to think about when trying to answer or investigate this, the question of the network depth, adaptability, is the first point is the forward pass. So the network has a forward pass and we have the backward pass, okay? So in the forward pass, we need to look at the activations. The activations, you go from, all these kind of building operations or blocks, and you're going to get the final activation, H3, H4, et cetera, okay? So the second thing is the gradient. So when in the backward pass, you need to look at the gradient. So the forward pass, we calculate the activations, okay? So we pass the data through the network. And in the backward pass, we collect the gradients. And we have seen that in the backpropagation lecture. and this one for the activations in the very first FCN and MLP lectures, okay? So now these two components may cause, one of them or both of them, they may cause big issues. So what are these issues? First, when you look at the change of the activation from layer to layer, so you have different layers, okay? So these are connected, all right? And then when you look at the changes of the activations here of different units and the activation from L to L+1, you want this change or this variance, okay, the change between layers to not be very high. So you want the delta A to be kind of stable. Because if you have a fluctuation in activations, you're not gonna learn something meaningful. Like it means like your neurons are all over the place. They are like firing, they're overly active, the change is high, so in this layer, you have a lot of firing neurons, and next layer, you have kind of dead neurons. So that's not good. This kind of discrepancy, this gap between two layers is not that good. Okay, so there's another thing. So in the backward pass, now to update the weights in the layers, we know that to update these weights, which control the activations, we need to do back propagation. So in the back propagation, we calculate the derivative of the loss with respect to the weights, okay, in a particular layer. So let's say, the weights of layer L. So here, when we look at the weights, the change, of the gradient between two layers, okay, so this change, let's call it DL, DWL, and then versus DL, DWL+1. And we compare these gradients in terms of magnitudes and also in terms of directions. And we will see that the magnitude particularly is very different, which means somehow you have big jumps, you have high changes in your loss, and sometimes you have very low changes in your loss. And that is not good also for the optimization of our network and for the learning of the optimal mappings right here, the W layers, okay? So these transformations basically of the data in a new representation space. So the idea is that, okay, so if we want to go deep, we need to make sure that somehow we're controlling these two variances. We're controlling the variance of the activations, and we're controlling the variance of the magnitude of the gradients between different layers. So we need to somehow stabilize the network. So we don't want, of course, we don't want them to be the same. Otherwise, you're just passing on the same thing. We want them to be different. So we have diversity in learning. So we want the different, functions or the different layers to be, to change a little bit. So F1, F2 should not be equal to F3, for example, but it should have some meaningful changes that will allow us to learn different kinds of transformations in mapping, but they should not also be very different. So divergent would mean like, completely different. So we don't want to stipulate this behavior. So these two extremes, total equality and complete inequality, these are two extremes, and we want our solution to float between, both extremes. Okay, so we want to find a balance. We want to find a sweet spot there. Okay, so how to do that? So let's look at, these problems. So actually, when we make the residual network deep, we have a problem, and its current format right here, the way it was designed, okay, or introduced, we will have an exponential or an exploding gradient. So we will have like a gradient explosion, especially towards the very end in the final layers. So why is that? So this exponential increase in the activation magnitudes is actually observed here. So let's look at this F. So this F has, we said a ReLU, right? And we have a linear transformation encoded by W. So every time you apply a ReLU and a linear transformation, what's going to happen is that because you're adding the same signal back here, you're adding the same signal. So somehow you're magnifying the values here. So every time you're going to apply a ReLU, the signal that goes into the ReLU function, which is the first, operation in this building block, in the blue block. So let's choose the same color. So the ReLU is the first operation in this block. And oops, it's not kind of, yeah. So when we input the data, it will be magnified because we're passing on the same data over here. So next time when we have the ReLU, it will get a strong go signal. So what does that mean? It means here in this first layer, for example, in F2, we're gonna get X2. So X2 is right here. So the activation of the ReLU would be over here, okay? So that's the ReLU, and this is max 0x. So this is, our ReLU function. So let's choose a different color, blue. Okay, so this is our ReLU function. Okay, so in the next layer, you pass on the X2 and you do some, you do the transformation and all of that, and then you're gonna take the X2 and then you're gonna add X2 to the output. So somehow this X3 that I'll output it, right? So the X3 has the X2 plus another signal, okay? So you can see, so every time the output is the input, the input itself plus a certain transformation. So you're making your values bigger and bigger and bigger. And as you make your values bigger and bigger and bigger, what's going to happen is that your activations, as you add more residual blocks like this with this kind of operation, right? Self-feeding operations, a self-feeding operation or self-increasing operation, you're going to end up with an exponential increase in the activation of the magnitudes, okay? So that's not a nice behavior to have in the network because as you have different activations, so then it means that the difference between two layers will be very high, and the distance between a few, a few layers that are, a few steps apart, it will be even higher, okay? So you will stipulate a large variance in activations in your network, and that will not stabilize the training of your network. So here, the variance in residual networks. So let's try to summarize this. So first we have what we call the head initialization. So I mentioned this last time. So the head initialization, if you guys remember, so we mentioned it, let me find where, so right here, yeah. So for ReLU activation, it initializes the biases beta to 0, and it and samples the W's, the weights at initialization from a normal distribution centered around 0 and of standard deviation 2 divided by DH, where DH is the number of hidden units in the previous hidden layer, okay? So this kind of initialization tries to control the variance of the weights. So everywhere in your network, you're stipulating the same sort of initial a normal distribution with slightly varying width depending on the number of units, okay? So as I explained here in the previous video, okay? So somehow you're controlling the variance between two consecutive layers. And the variance between two consecutive layers is controlled by this factor right here. So this hit initialization allows us to kind of decrease the variance when we, or control the variance when we are initializing the network. So moving forward, so let's see what happens. So with this hit initialization right here, so it ensures that the expected variance remains the same after a linear plus ReLU layer, FK, okay? So unfortunately, in residual networks, the output of each block is added back to the input. So the variance doubles at each layer. So you can see it here. So it's going to double at each layer somehow. So doubling is kind of not very exact, but it will kind of increase. And it's a sort of a doubling effect because we're adding the same thing. So they called it here doubling, but mathematically it's not perfectly, doubling. But anyway, so it kind of increases, but let's say it doubles. Okay, so the variance doubles at each layer and grows exponentially.
All right. So now let's look at the second case. So in the second case here, we added so it's the same network, but in this network, so I'm going to remove these guys. So in this network, we have basically added a new factor, a new weight in our network. Okay, so to weigh or to kind of neutralize the residual output. So every time you get your residual output, you apply a multiplication by 1 divided by the root square of 2, okay? And then what happens here is that you are decreasing the doubling. So we have a doubling that happens, right? Remember, in every single at each layer output. So we want to kind of neutralize that. And to do this neutralization, we're going to rescale the signal by this quantity. And this allows us to kind of tone down the, the x squared, okay? So here in this example, in solution B, this is an intermediate solution that allows us to kind of control the activations and not having, or pushing towards an exponential growth of these activations. So this simple operation right here, it would have been nice, if I asked you first, oh guys, how can we solve this? Okay. So, and if you take some time to think about it, you'll say, okay, something is happening here. So there is a problem over here. How can I fix this problem? So one way to fix this problem is to kind of act or introduce an action at that level to fix what you have created or the network has created. So you're trying to kind of fix the problem. And to fix the problem, here you can add this multiplication. So that's one way. All right. Now, the best way or the most common way is to use what we call a batch normalization. And we have seen batch normalization also in the previous lectures. And it's a very common concept. It allows us to kind of regularize the loss, speed up the convergence. We have seen so many beautiful properties of batch normalization and how it exactly works and why we introduced it. But today we're going to expand a little bit more on that. So batch normalization is fundamental for all networks, in particular residual networks or residual blocks. So within a residual block like this, it is very important to add a batch normalization before your ReLU and before your linear layer. Okay, so you normalize the data that is the output of the previous layer. So you do the normalization of the data, the output of the previous layer. So here it would be H2, right? So you normalize these hidden units, all hidden units that you have, and then you apply your transformation. And then when you feed back, basically here you feed back the original data, not the normalized data. So there is always, when you're adding this residual connection or the skip connection, you're adding back the original data, okay? Maybe you can also try and reason about adding, this part right here. So this is another question. So what would happen if I add back, the normalized data? You're going to lose the scale of the original data. That's what's going to happen, because when you normalize data, you're changing the distribution, the mean and the standard deviation. So if the original data looks like this, right? And then you're forcing it to fit a distribution like that with the BN, right? You're completely changing the distribution of your data, and you cannot recover it, because every time you're going to feed the network, the residual connection comes from the BN normalized data. So one threat to your data distribution, if you want to preserve the data distribution, like for example, in biological data, you cannot simply shift the data from 0 to 1, like scale it easily. So you normalize, but you need to recover the original data. And also generative AI, you need to generate data within this kind of distribution that varies maybe between, I don't know, like 11 and
22.7. So you need to be, careful about where to put your skip connections. And if normalization doesn't really matter to you, maybe you can do that too. So this is something you need to think about and, build a logical narrative as to why, and rationale as to why you're introducing the skip connection after the BN and not before the BN, okay? And this applies to both, of course, solutions. So now let's look at this C. So in the second, basically in this C solution, it's a second method that is used, that we use, which is batch normalization. So we use BN as the first step in the residual block and set the associated offset delta to 0 and scale gamma to 1. So we'll talk about these parameters in just a second, or in a minute. So this basically transforms the BN, transforms the input to each layer to have variance 1. And we with the hit initialization, the output variance will also be of 1. So what is happening here, that the variance, the sigma of the input I, and the sigma of the output J will be, the same. So basically they will be the same, and we're controlling the variance. So in this case, with these BN blocks, we are able to kind of control the variance. And the variance in this case of the activations, of course, they will increase linearly with the number of blocks. So a side effect to this is that the later layers of the network make relatively smaller contributions. So why is that? Because every time you're controlling, so imagine, so it's actually very logical. So what is happening here is that each BN, so at the beginning you have a very different, like kind of funky distribution, and then you're forcing each layer to have a similar distribution. So somehow you're going to have some changes here. The delta A between layers I and layers I and J. But towards the very end, your change, or the variance in your activation between the final layers, let's say big L minus 1 and L, this will be very low, because somehow you're forcing everybody to be similar. So at the beginning, you're going to learn something, but as you add more layers, you're going to learn the same thing. Okay, and this is what we talked about earlier, guys. We talked about this kind of balance. So you don't want to learn the same thing. You don't want to, control the variance, have exactly the same variance, set. Because if you have that, your network may not need a lot of deep layers, because you're going to repeat the same mappings. You're going to learn the same kind of, transformations, very similar. And that is not a nice thing to do if you want your networks to get deep, okay? So these are very important points. And now let's look at the, let's try to summarize this, okay? So here, if we reason about activation, so activations, of course, they happen in the, during the forward pass. So during the forward pass, each of the two branches has what we call an independent variability. So each of the two branches of the residual network, this is the first branch and this is the second branch, they have independent variability. So the overall variance increases when combined together. So when we combine them, we're going to have higher variance. So this has, for example, variance delta, and this second branch here, variance delta prime, and you're going to have an additive variance delta plus delta prime. So this is another way of looking at this also, how can we explain the, the increase in activations in general, regardless of the type of activation, not just ReLU, because ReLU takes max 0x, okay? So with the initialization, the head initialization in ReLU, the variance doubles with each residual block. So we have an exponential growth of the variance as we add more blocks, and we explained this earlier. So how to induce a counter effect, and this is what we try to solve. So this is a recap. So we induce a counter effect to the doubling by multiplying by the square root of 2, okay? And then we have also, we can add a BN block. All right, so these are two different options. And you can think about maybe a third option, and this could be a better solution. How can we counter effect? How can we, induce this counter effect in the network to kind of, tone down the activations? Okay, so now the second point, what we have seen that, well, this logic also applies to gradients. So we didn't actually see this, but I mean, the way we reasoned about activations, you can reason also about gradients. So gradients, as you collect gradients backwardly, you may end up with, exploding gradients. You're going to have a variance in your gradients, okay, and the gradient magnitudes. And this variance is not good to have. So it's a similar things. Because of the skip connections, you're going to have this kind of cumulative variance in your gradient magnitudes from layer to layer. And you can actually see it here. So, the first layer, the second layer, third. So this is cumulative. So you have completely different, you're adding up different things. So when you compare the first layer, okay, and the second one, etc. So you can see that comparing identity with this quantity, so there is a big delta here. There is a huge gap. Okay, so this is also expressed mathematically. So you can see that very clearly. So now the network, the residual network, without the BN, without the batch normalization, suffers from two things. It suffers from an explosion in its activations due to the residual connection. Same applies to its gradient, also because of the residual connections. So it suffers forwardly and also backwardly. All right. So we have seen different solutions to compensate for the doubling, and one of them is BN. So now let's look at this batch normalization. So how do we actually introduce it in residual networks? So it's actually very simple. It's the same way that we introduced it before. So for batch normalization, the batch norm, it shifts and rescales each activation H. So every single hidden unit, that is the output of, the W layer, and also, for example, nonlinearity such as ReLU. We do some shifting and rescaling. So we bring everybody to the same mean and variance across the batch. This is during training. So remember, guys, we split the data into different samples, and we call these batches. So we have batch one. So we have seen this before in the previous lectures. And you have, for example, B and batches. So for each batch B, we will try to strike, the same, we will try to have the same kind of, mean, and to rescale each element to the same mean and standard deviation. So here, what we are actually shifting and rescaling is the activations of our neurons in our layers. So these are the neurons in our layers, and we're trying to kind of, create a normalization using the batch that we have, okay? So first, we need to calculate the empirical mean, MH, and the standard deviation, SH. Okay, so the empirical mean, we take all elements in the batch of the current layer, and we basically calculate the mean HI for over all elements I in the batch. Okay, in in the current batch. So we calculate the mean and the variance of this particular unit. So here we will sum HI over all I samples in the batch. All right, so our training samples in the batch, and we'll create a mean value for the unit, for our units, and then the for our batch, and also the SH here for the batch. Okay, so after we get the standard deviation and the mean, we simply normalize the HI. So for every single unit now in our layer, so for each unit HI, so these are units, we're going to subtract the mean and divide by an SH plus an epsilon. Okay, so this is normalization. the normalization happens here. So this is, you know, we kind of normalize or with respect to the mean and standard deviation. So why we're adding a an epsilon? So the epsilon, it prevents division by 0. So if we have, for example, two values that are identical, hi and, for example, hj, right? For two elements in the batch, for two samples, training samples, I and j. So these are training samples. So if we have exactly the same response for these two training samples, let's say all of them are exactly identical. If we happen to have very similar samples in the batch, then you may end up with a 0 because the standard deviation here will be 0 and you don't want to divide by 0. So what happens is that we add this epsilon right here, okay, to avoid the division by 0. So now the next step is the most important step. Now this will have a mean of 0, 1, right? So like, so this will kind of normalize the data, but we want to control the variance, okay? And we want to control the variance and the standard deviation of each layer. So let me explain. So if we have the first layer, so this is our layer L, and we go to, these are the hidden units, to layer L plus 1. And here, if we have exactly the same variance, 0, 1, okay, so and 0, 1, so this will be identical. These guys will be identical because of this kind of, you know, normalization. All right, so we brought everybody to kind of, you know, this kind of a fixed, the same distribution. So this is not really good because, as I mentioned, you will completely remove the variability between consecutive layers. You're going to end up with identical distributions, and this may not be something good for your learning because you want to have some diversity in your weights, in your layers. Okay, so you want to promote diversity in your layers, and to promote diversity in your layers, between your layers, then you can try to control the standard deviation and the you know, the standard deviation and the mean of each layer. So what you're doing, you're taking this kind of, you know, distribution right here, and you're shifting it, or you're kind of making it narrower right there. So you're introducing for each layer a scaling you know, factor, gamma L, and a shifting factor, delta L, and you're going to do the same, gamma L plus 1 and delta L plus 1. All right. And here you're going to do this, you know, you're going to learn this for each of your units. So here, for every single unit, you're going to actually shift it by a gamma, scale it by a gamma, sorry, and shift it or offset it by a delta. So the activations here will have, in this case, the activation that we have right here will have a mean of, the delta will be the mean, and the gamma will be the new standard deviation across all samples in the batch. And here, if you guys know this, when we do the BN to each hidden unit, if we have a K-layer network with D units, how many gamma and delta we need to learn. So if we're going to do that for every single unit, so we're going to shift this, you know, for each, we can do it per layer. We can do it per layer like here. So if we do it per layer, we're going to have K units, of course, K gammas and K deltas to learn. But if we're going to do it at a more finer scale, which means we will make the delta and the gamma depend on the unit, which means we'll allow the units here to have slightly different distributions, right? To be drawn from different distributions to capture different properties. Then we're going to learn K times D, because we have K layers and D units, hidden units in each layer. So we're going to have KD extra hyperparameters to learn. Okay, so you can do it both ways. And usually it is done in this way. It's more computationally expensive, but it allows your network to kind of be normalized, but also have a sort of flexibility, a shifting and a scaling effect that allows you to capture different patterns in the data and not exactly the same patterns from layer to layer. Okay, so that's how, you know, different patterns will get captured by different layers. It's thanks, you know, to, you know, the weights, of course, but the scaling here, the batch normalization controlled by these extra parameters. Okay, cool. So there is a lot that comes with batch normalization. It's not as simple as it seems. It's actually very powerful, and it plays with the statistics of the hidden units distribution across the batch that we're training on in each iteration until we complete the full epoch. Okay, cool. So now let's summarize this. So we're going to summarize here very nice points about the batch normalization. So let's start with the first one. So the first one is like when you use batch normalization, you have a lot of benefits. The first benefit is that the batch normalization makes the loss surface and its gradient change more smoothly. So it's kind of, you know, it reduces the shattered gradient. So this is a problem that is nicely solved. The problem of the shattered gradients that we talked about earlier, it can be solved with BN. Okay, so batch normalization is actually the solution and not the residual connection only. Okay, so the residual connection helps at the beginning, but if you want to make your network deeper, so residual connection is good for this. Okay, residual skips, they are good, but if we get deeper, as it gets deeper, so with depth, they become not good. Okay, so you need to kind of use batch normalization to solve that, and this is the logic behind this. So one can also use higher learning rates as the surface is more predictable and smoother. So which means if your training surface, if your loss function is smoother and it's not like kind of, you know, very zigzaggy, then you can use a large learning rate. So if you have a gradient right here, you can just use multiply the gradient by, you know, the negative of the gradient of the loss, L, so negative of the gradient, by a factor of eta, and eta will make your gradient jump, you know, so eta is large, so you can just converge quickly, right? Because it's kind of smooth. But if you have an eta of the same length here, so you're going to kind of maybe miss a good optimum. So it doesn't work on kind of, you know, very, I would say curvy or like very highly changing surface, okay? So the second point, so that was the first point. The first point is that higher learning rates. So we have higher learning rates. And then regularization. So BN, it injects noise to the training process. So you can think about BN as a noise injection. So why is that? So let's keep on reading. Because the normalization depends on the statistics of the entire batch, right? So the statistics of the batch, they do, you know, control the batch. If we have a batch B, they do the statistics, which is, you know, the gamma, so the mean and the standard deviation, okay, that we talked about. These are, they control the normalization of the H, right? So somehow the normalization depends on these statistics. So it's not kind of, you know, it doesn't depend on universal statistics. So every time you're normalizing with respect to the batch, so somehow we're considering that, you know, these changes in the statistics, they will induce, you know, a sort of a noise, like the change between batch 1 and batch 2, batch 3. So that kind of introduces it acts as a noiser to your network training, but it's a good noise that allows you to generalize better. So there are some studies, by the way, that showed that injecting noise makes models generalize better. So for example, so the activations of a given training sample will be normalized by an amount that depends on the members of the batch. So if we have X here, and we feed X as a single member, and X happens to be in this batch, so let's call this batch B. This batch B has all these samples. Each sample belongs to RD, D-dimensional features, right? It has D-dimensional features. And then we feed this sample, so this is our sample X, that we feed into the network. So what happens here is that, you know, when we, the activations that happen after this layer, so the activation, the final activation, well, actually we have it right here, the final activation H2, right? It is normalized by an amount that depends on the member. So it is controlled somehow. This activation right here is because of the BN, is controlled by these members, the other members in the batch. Okay, so it will be processed slightly differently depending on the batch elements. So this is what we call it kind of noise. So every time you have a different batch, so if I have another batch right here, and let's put, for example, different colors. So these are my elements right here. And if I input, you know, my data, so the distribution now, I'm going to look at the distribution inside this batch, and this distribution will be different. The purple will be different from the, you know, from the orange distribution. So somehow the distribution of the purple, I'm gonna do it like maybe like this. Okay, so the distribution of the orange is somewhere around that. And what happens that every time you're taking the mean, here the mean and the standard deviation of this distribution, and then the mean and the standard deviation of the other, and then these will kind of be different, okay? So because of that difference, the normalization or the activation here will differ depending on the batch. So, you know, so a given sample, if it is put in a completely different batch, it will be normalized differently, and that's why we call it somehow noise. So this batch right here acts as a noise because the elements there, they define the guy, right? They define the main sample. So if you end up with completely different guys, your activation, the activation H2 of sample X, you know, when X belongs to B, will be different or slightly different from the activation H2 of the same X when X belongs to B prime. Okay, so that's how we articulate it mathematically. All right. So it's something to ponder over, you guys. You don't need to get like in depth right now, but the more you think about it and the deeper you think about these statements and you kind of try to write it mathematically and simulate the training process in your brain and see the distributions, you'll be able to understand this better, okay, and deeper. Now, we have seen two benefits of batch normalization. So the first one is higher learning rate, regularization. And the third one is stable forward propagation, okay? So stable forward propagation, it means that, you know, the variance of the input activation. So we talked about the variance. The variance of the, so we know that in residual networks, the variance of the output activations will increase as we add a new source of variation to each, you know, to the input of each layer. So we know that, and this is what leads to the explosion of activations as as the network deepens. Okay. So, however, it will increase linearly with each residual block. The kth layer adds 1 unit of variance to the existing variance of k. So this is what we have seen. So when we add the bn kind of controls the activation growth. And this is the good property of bn. So this should be all in kind of green color. So this is a nice property of bn, that it fixes or controls this activation growth. And by controlling that, the activation happens during the forward pass. So it's the forward problem. And now with Bn, we have solved the forward problem, okay? So we have basically toned down the activation. So here in the first case, we have an explosion, a forward explosion of activations on neural responses. And here we have more controlled thanks to this multiplication or de-doubling. And with Bn also we have a nice control using the batch normalization. So these are two good solutions to this problem. So another point to add at the end of this is that, the later layers, they make smaller proportional change to the overall variation than earlier ones at initialization. So the problem with this Bn that somehow we're going to, this is not a good effect. So the later layers, these later layers will not contribute, much to the learning, okay? To the learning. Why is that? So this is also explained. Remember when we said, for example, we'll go from H3 to H4, and we have the delta, which is, H, which is H4 minus H3. If this is identical, then, there is no variability in the learning. So, kind of same learning, no difference between the layers. The layers are similar. Layers are quite close, okay? And here, when there are two different, we have a divergence here, divergent layers, and they're not correlated. There isn't anything between them that there's big jumps. And these are two extreme behaviors, as we talked before. So in this case, when we are controlling with Bn, with this batch normalization placed right here before the learned linear transformation and the nonlinearity, then we end up with somehow learning very well in the first layers, but the last layers will not learn very well because they're going to somehow copy the early layers as they will have very similar distributions. So somehow as the network gets deeper, you're going to repeat the same thing over and over again. So it's not learning, it's kind of parroting. It's becoming a parrot. It's just, like replicating, okay? So that behavior is not that good because you're not going to learn a lot in the final layers, or you're not going to discover new knowledge in the final layers, okay? So that's the one point. So the network, so let's keep reading. So hence the network is effectively less deep at the start of the training, since the later layers make negligible changes. So as the training proceeds, as we keep on training the network can increase the scales, gamma, in later layers, and the network can easily control its own effective path. So which means somehow, because here in the Bn, we have introduced new parameters. So we have the gamma and the, so we have the delta and the gamma. Okay, so the gamma and the delta. So if these vary a lot in the last layer, if we learn them very well, if we learn different, shifting and scaling factors for each hidden unit, if we are able to learn them well, then we will have diversity. So one thing here, if delta and gamma are learned because and optimized well, then we can have effective deep or later layers, because they will be, they will introduce some variance, they will introduce a sort of controlled variance, okay? So controlled variance, and this is an important word here because we want to control the variance. Okay, so that was pretty much it about, residual networks. So we have a good story here. We can make our residual networks deep, but to make them deep, We need to use, BN. It solves the shattered gradient problem. It solves, the bad training. But we need to also make sure that we're learning the hyperparameters, the scaling, and the shifting and the batch normalization very well. So you guys can see that batch normalization is actually very powerful, because without it, you cannot deepen your network. And without it, you cannot have a good training of your network. Okay?